At trends in the periodic table, and our learning intentions are to explain general trends in atomic radii and first ionization energy, and then to discuss second ionization energy and the existence of energy levels. Okay, so to start this video, it's important to know what a group and a period is. So a period, they go across the periodic table from left to right, and a group goes down the periodic table. So the first trend we're going to look at is atomic radius. And the definition for atomic radius is the atomic radius of an atom is half the distance between the nuclei of two atoms of the same element that are joined together by a single covalent bond. So if we look at a diagram here, in a hydrogen molecule, the distance between the two nuclei is 0.74 nanometers, so that is 0.37 nanometers as an atomic radius. So we start at the center and we go to the center. And the atomic radius is then half of that. So for our trend in atomic radius increases as you go down the periodic table or go down a group, and that is because, first reason, we have new energy levels. So additional electrons go into new energy levels which are further away from the nucleus. So basically each time you go down to a new row in the periodic table, you're getting a new energy level. There's also screening of inner electrons. So electrons on inner energy levels shield the electrons on outer energy levels from the positive charge of the nucleus. So that basically means that the electrons are not pulled as tightly into the nucleus. So as you can see with my diagram here, this outer shell, it's further away from the nucleus because the positive charge that's coming out from the nucleus has further to travel. So it's going to lose its positivity as it moves outwards to try and drag this outer shell in. And the easiest way to think of it is, let's say, like people gathering around a heater. The people that are closest to the heater here at the centre will get the most heat, and the further you are away, the less you feel the heat. If we look at going across the periodic table then, we can see that atomic radius decreases as you go across. And there's two reasons for this. The first one is there is an increase in the nuclear charge. So that basically means the number of protons is increasing as you go from left to right on the periodic table. So there is a greater attractive force for outer electrons. So energy levels are pulled closer to the nucleus. So if we look at my example here, if as we go across a period, we have electrons being added to the same energy level, but they're being added to the same energy level while the charge of the nucleus here at the center increases. So it is able to pull these electrons closer towards the nucleus because the electrons have been added to the same shell. The second reason for the decrease in atomic radius as you go across a period is there's no increase in the screening effect. And this can be explained here with this diagram that I've drawn as well. Extra electrons are added to the same energy level. So there's no increase in the screening. The electrons aren't any further away from the nucleus. So basically the electrons in the same energy level experience similar screening effects. The second trend that we're going to look at is ionization energy, and the definition for ionization energy. The first ionization energy is the minimum energy required to completely remove the most loosely bound electron from a neutral gaseous atom in its ground state. That definition needs to be learned word for word because every year students leave out gaseous atom, neutral or ground state, and as a result lose marks. So basically ionization energy is the tendency of an atom to lose an electron. That's what it is in simple terms. So to help explain ionization energy in more detail, I thought I'd just show it to you in a balanced equation. Ionization energy, as you can see here at the start, we have a neutral sodium atom, and the sodium atom has lost an electron, so it gains a positive charge. That's our first ionization energy, but here you can see we can also have a second ionization energy, where this original sodium in the first ionization energy, the Na+, becomes the reactant for the second ionization energy, and it loses another electron to become Na2+, and to produce that another electron. So the second ionization energy refers to the energy required to remove an electron from an ion with a positive charge in the gas state. It's very important if you're asked to do balanced equations or any sort of equation for ionization energy that you include the gas symbol, as ionization energy refers to things in the gas state only, as we've seen in our definition. So if we look at the trends in first ionization energy, it decreases as you go down the group. And this is due to an increasing atomic radius. So the atomic radius increases as you go down the group. So the outermost know that these less attractive forces happen due to our second reason, which is the screening effect. Electrons on inner energy levels shield the electrons on outer energy levels from the positive charge of the nucleus. So even though nuclear charge increases, this increase is counteracted by the shielding, because as you go down the periodic table or go down a group, you are gaining new energy levels. So as you can see from the little diagram I've drawn, these outer electrons are an awful lot easier to move, because A, they're further away from the nucleus here at the centre, but also they don't feel the positive charge as strongly due to screening from these inner electrons. First ionization energy increases as you go across a period, and this is due to an increase in effective nuclear charge. So again, the number of protons increases from left to right, so there is a greater attractive force for outer electrons. There is no screening. So energy levels are pulled closer to the nucleus, meaning more energy is needed to remove the electron. Like at the last slide, we can explain this by saying that the electrons are added to the same energy level each time, so there is no additional screening. Secondly, we can say that there is decreasing atomic radius, and the atomic radius decreases from left to right, so electrons in the outermost energy level are pulled closer towards the nucleus, meaning more energy is needed to remove them. And this again can be explained with this diagram, because the electrons have been added to the same energy level each time, so there is an increased positive charge and the electrons are not getting further away by going into new shells. There is certain exceptions to this trend for ionization energy, and some elements don't follow the smooth increase. For example, beryllium and nitrogen have higher values than expected, and this is because any sublevel that is completely full or half full has extra stability, and we've already seen this in our D block electronic configurations in our video on electronic configurations. Looking at ionization energy can also further show us evidence for energy levels existing, and we're going to look at this in the next slide with a graph. So if we look at this graph and we start here at the beginning, we can see this is first ionization energy. This first little yellow dot here is hydrogen. And as you can see, the ionization energy increases as we move across to helium. It's very high there. But if we look and go to the next element, which is lithium in the periodic table, the ionization energy drops down significantly, and that's because in the helium it has a full outer shell, so it's very difficult to remove an electron from a full outer shell, as it has very stable. Where lithium has one electron in its outer shell, it's further away from the nucleus, so it's easier to remove. We can then see with the rest of these dots that I'm highlighting now that our trend ionization energy increasing as we go across a period, and we get to neon, and we can see here that it is a high first ionization energy, again because it is a full outer shell and it doesn't want to lose any of its electrons. If we then move to the next element, which is sodium, we know that sodium has one electron in its outer shell. It has now got an increased atomic radius because it's got a new energy level, so this one electron is easier to remove. So we can see this more clearly when I draw out the electronic diagram. We can see that neon has a full outer shell, but with sodium there is one electron in the outer shell and it is now also further away from the nucleus, creating lower ionization energy, meaning the electron's easier to remove. So some general points to note from that last slide, that there is a steady increase in ionization energy values. Nucleus and the remaining electrons. The positive ion is smaller than the neutral atom, so electrons are closer and more attracted to the nucleus. However, as I've also said, we can see a large increase in ionization energy when an electron is removed from a full energy level. A larger increase when a new sublevel is encountered due to the extra stability. So that's it for this video. Read over the learning intentions to make sure you understand everything we've gone through.